Good morning. Uh, in the what we've done till now in equations and inequations essentially is we looked at the wavy curve method, and we saw that how we using the wavy curve method, a large number of inequalities can be solved. Specifically, inequalities of the form rational function greater than, less than, greater than equal to, or less than equal to 0. Whenever you have such an inequality, you can use the wavy curve method. And of course, we had seen the different kind of cases and the different kind of steps that have to be followed in applying the wavy curve method. And of course, in the chapter on quadratic equations, we've already seen the idea of solving quadratic inequalities. Now we'll be introducing the concept of modulus, which is very important from the point of view of competitive exams. So we'll be introducing the definition of the modulus and then looking at how to solve modulus-based equations and inequalities. Now, at a very basic level, I think everybody's you guys would have a slight idea about the modulus of a value. Whenever we talk about the magnitude, the modulus of a number, we are essentially talking about the magnitude of that value. That is to say that we are not interested in the sign of the value. So magnitude of the value 2 or mod of 2 happens to be the value 2, and similarly mod of the value minus 2 also happens to be the value 2. That is to say that for a modulus, the output, how will you kind of decide what the output of the modulus function is? If the input itself is something which is positive, the output will remain exactly the same, and if the input is negative, you will have to multiply the input by a negative sign, thereby kind of getting rid of the negative sign, right? So if you want to now define this on in a more general way, this is how we could do it. So we could start by saying that the modulus of any given value x, of a real value x, will be defined as, again from the example that we saw, so this is the general definition of mod of x, right? Mod of x is equal to x if x itself is greater than or equal to 0. So again, if the input itself is something which is non-negative, which already is greater than or equal to 0, the output will also be greater than or equal to 0. On the other hand, if the input itself happens to be something which is negative, you will have to multiply the input by a negative sign so that the effective output becomes positive. So taking the 2 example, mod of 2 of course will be 2. We'll be using this definition since 2 is positive. And when you're talking about mod of minus 2, since minus 2 itself is negative, I'll have to multiply it by a negative sign. Right? So this basic way of splitting the modulus now becomes something which is important. Right? Instead of x, of course, you could have a general function, but the basic idea will be the same. Mod of any expression is equal to that expression, would be general mod of some expression f of x. So you can easily extend the definition, to kind of talk about a more general scenario. So f of x, if f of x is any function, then mod of f of x will be f of x itself for those values of x for which f of x itself is greater than or equal to 0, and it will be minus f of x for those values of x for which f of x itself is less than 0. So this kind of becomes important, this ability to split a mod term into f of x or minus f of x depending on the value of x is important from the point of view of solving some problems. So for example, if you want to split the value of mod of x minus 1, I could say that mod of x minus 1 will be x minus 1 as long as x minus 1 is greater than or equal to 0, and minus of x minus 1 if x minus 1 itself is less than 0. And of course, x minus 1 greater than or equal to 0 itself means that x has to be greater than or equal to 1. And x minus 1 less than 0 itself has to mean that x is less than. So this would be the split for the mod x minus 1 term. So similarly, you would have had a quadratic expression also, or you could have had 2 linear terms. So for example, now suppose your function, your entire expression is mod of x minus 1 plus mod of x minus 2. Over here now there are 2 terms. This will change its definition at 1, right? Mod of f of x changes its definition whenever this f of x will be 0. So x minus 1 over here itself is, the first term changes its definition at 1, and the second term changes its definition at 2, right? So we'll have to take, so effectively if I consider the number line, there are 3 different intervals that I'll have to talk about. The values of x which are greater than or equal to 2, the values of x between 1 and 2, and the values of x which are less than 1, right? So these are 3 intervals. And then you kind of keep going. So now if x is greater than or equal to 2, then x is also obviously greater than or equal to 1. So mod of x minus 1 will be x minus 1, and mod of x minus 2 will be x minus 2. So effectively you get 2x minus 3. On the other hand, if x is less than 2, then x minus 2 becomes negative. So mod of x minus 2 will be minus of x minus 2. And mod of x minus 1 of course remains x minus 1. Because since x is greater than equal to 1, x minus 1 will be greater than equal to 0. So mod of x minus 1 remains x minus 1. And when we go to the x less than 1 case, if x is less than 1, then x minus 1 as a value is negative, and x minus 2 as a value is also negative. So mod of x minus 1 will be 1 minus x, and mod of x minus 2 will again be minus of x minus 1 and minus of x minus 2. And so finally you can say that for mod x minus 1 plus mod x minus 2, the value of this expression can be split up into 3 cases. For x less than 1, it will turn out to be 3 minus 2x. For between x, when x is between 1 and 2, interestingly, the entire expression is turning out to be a constant equal to 1. And when x is greater than equal to 2, you're getting the expression 2x minus 3. Let's take another example. Suppose you have this term mod of x square minus 5x plus 6, and we want to split the definition. So again, following the basic idea, this should either be x square minus 5x plus 6, which will happen if x square minus 5x plus 6 itself is greater than or equal to 0, or minus of x square minus 5x plus 6, which will happen if x square minus 5x plus 6 is less than 0. Now we'll further have to kind of figure out which are those values of x for which these conditions themselves are satisfied. And for that, of course, we could go to our wavy curve method again. So x square minus 5x plus 6 is greater than or equal to 0. That itself will happen if so again, product of two linear factors, coefficient of x is positive in both the factors, critical points are 2 and 3. The way would be something like this. Greater than equal to 0 would happen over here. Right, so it's turning out that x square minus 5x plus 6 will be greater than equal to 0 if x is less than equal to 2 or greater than equal to 3. And similarly, x square minus 5x plus 6 will turn out to be less than 0 if x itself lies between 2 and 3. So I can now finally reduce this definition to saying that so mod of x square minus 5x plus 6 will be x square minus 5x plus 6 if x is less than equal to or if x is greater than or equal to 3. And mod of x square minus 5x plus 6 will be minus of x square minus 5x plus 6 if x itself lies between 2 and 3. Right? So again, this idea of given term of the form mod of f of x, being able to split it up into f of x or minus of f of x is important. What we'll now do is we'll come up with a base list of basic properties for the modulus operator and then use them to solve equations and inequalities. The first property, of course, follows from the definition. Mod of x for every real value of x will be something which is always greater than or equal to 0, and specifically it can be equal to 0 if and only if x itself happens to be 0. At this point, I also want to mention one thing. Mod of, in terms of real values, the mod of a real number x can also be given a certain geometric interpretation. So, if we look at the number line, then 0 is over here, and of course you have positive values over here and negative values over here, and of course you have, all rational and irrational terms plotted over here. So when I talk about the mod of 2, and if I talk about the mod of minus 2, their values are the same. So geometrically, what I could say is that mod of 2 and mod of minus 2 both represent the distance of mod 2 is at a distance of 2 units from 0, but on the right hand side. Similarly, minus 2, the number minus 2 is also at a distance of 2 units from 0, but on the left hand side. So in that sense, now I can give mod of x a geometric interpretation, and I can say that mod of x represents the distance of the real number x from 0 on the number line. Second basic property, which is quite obvious, is that mod of minus x is the same as mod of x. Right? So negative signs inside the modulus can be, you can kind of get rid of it. Property also is quite obvious that mod of x whole square and x square will be the same value for all possible values of x. So even if I put x equal to -2, I'll get 4 on the left hand side and 4 on the right hand side. Right? This property is important in solving equations. So what we are saying over here is that if you square a modulus based term, you can effectively remove the modulus. Modulus turns out to be distributive over multiplication and division, which again can be verified by some simple example. Think about addition and subtraction. It's quite easy to see that modulus in general will not be distributive over addition and subtraction. So as a simple example, if you look at mod of 1 plus 2, that of course is equal to mod of 1 plus mod of 2. But if you look at something like mod of 1 minus 2, right, that is not equal to mod of 1 plus mod of minus 2. Modulus, therefore, in general will not be distributive over addition and subtraction. But what we can do is come up with a certain inequality which will always hold true. And it's an important inequality which kind of comes up in vectors and complex numbers also. So for two real numbers x1 and x2, what I can say is that basic inequality essentially will say that for any two real values x1 and x2, the mod of x1 plus x2 will always be less than equal to mod x1 plus mod x2. And mod of x1 plus x2 will always be greater than equal to this particular value. Right? I kind of look at this inequality and analyze it further. Specifically, we are interested in finding out that when will this particular equality hold true. So if x1 plus x2 is actually equal to mod x1 plus mod x2, then when does that happen? So let's take examples again simple. So again, if x1 and x1 and 2, it works for that, right? But if you have x1 as 1 and x2 as -2, then obviously you get 3 over here and 1 over here, so it doesn't work. And similarly, if you have x1 and x2 both, if you take x1 as -1 and x2 as -2, then you'll again get 3 over here, and mod of -1 is 1, mod of -2 is 2, and you'll get 3 over here. So again, the equality holds true. So by observation, this is turning out to be true whenever x1 and x2 both have the same sign. That is that they are either both positive or both negative. And of course, any one of them could be 0 also. So if x2 is equal to 0, then obviously mod x1, the LHS and this term and this term will become the same, right? So therefore, I can collectively now say that if x1 plus x2 will be equal to mod of x1 plus mod of x2, then I can directly say that x1 into x2, the product has to be greater than or equal to 0. This will include the possibility that either one of them is 0, and will also include the other possibility that x1 and x2 have to have the same sign. Similarly, if you think about the left hand inequality, if x1 into x2 is less than 0, that is to say that this will hold true if x1 and x2 have opposite signs. One of them has to be positive and one of them has to be negative. Now, since this inequality holds true for all possible real values, what I can do is I could replace x2 by minus x2, in which case I'll get something like this, that mod of x1 minus x2 is also satisfying the same inequality. Inequality basically will also hold true if instead of x1 plus x2 I have an x1 minus x2 over here. What will change of course are the conditions of equality on both the sides. Both the equality conditions will kind of reverse. So this equality over here will happen if x1 into x2 is less than or equal to 0, and this inequality over here will happen if x1 into x2 is greater than 0. They can be a less than equal to 0. Right. So for this particular inequality, this form, the reverse conditions will simply reverse, and you can keep extending this inequality. So mod of x1 plus x2 plus x3 must be less than equal to mod x1 plus mod x2 plus mod x3. Of this property, suppose you have this equation that you want to solve. You want to find those values of x for which this equation is satisfied. So an observation over here is that the equation can be rewritten in this particular form. Reduces to the form that we've discussed, that mod of x1 plus x2 is equal to mod x1 plus mod x2. So that again should be true if x1 into x2 is greater than or equal to 0. Now we can use the wavy curve method. Equal to 0, so x can belong to the interval -2 to 2 union 3. What you want to look at is that you want to look at some very basic equations and inequalities and come up with their solution sets, and using those ideas then we'll be able to look at more complicated equations and inequalities, right? So we have one equation and two inequalities, and you want to come up with the solution set for the variable x For the time being, we can assume that a is a fixed real value, but I mean some similar principles will be applicable if even kind of you replace a by another function of the variable x. The first equation, again we can think in terms of examples. Suppose a happens to be 2. So when I say that mod of x is equal to 2, then obviously x can either be plus 2 or minus 2. So for mod of x equal to a, I can simply say that x will either be plus or minus of a. And if a is negative, so for example a is minus 2, then mod of x equal to minus 2 will obviously have no possible solution because mod cannot be negative. So over here the answer should be a null set. Mod of x cannot be equal to a negative value. So again, as examples, if you have the equation mod of 2x minus 1 equal to 2, I can directly say that 2x minus 1 has to be plus minus 2. So taking a positive sign once, I'll get 3 by 2. Negative sign gives me minus 1. And similarly, if I have something like, if I have mod of x square minus 4 equal to minus 1, I can directly say that x cannot take any possible value because modulus cannot be negative. Now, in the second solution set, what we are saying is that mod of x is greater than a, right? So again, let's think of an example. Suppose I say that mod of x is greater than 2, right? We need to find the set of all values for which the modulus of x happens to be greater than 2. So obviously now x itself could be greater than 2, but then if you think about it, x can also be less than minus 2. So for example, mod of minus 3 is 3, which is greater than 2. So for mod x greater than 2, the solution set should effectively be that x can either be less than minus 2 or x can be greater than 2. And similarly for mod x greater than a, what I could say then is that x can either be less than minus a or x will be greater than a. Right? And if a is negative, then what do you say? So when I say, if for example again if a is minus 2, then if I want mod of x greater than minus 2, then I'll say that x can obviously take all real values. So when a is negative, the solution set becomes all real numbers. Now for the third case, when mod of x is less than a, again if let's say mod of x is less than 2, then obviously x has to be less than 2, but at the same time it also has to be greater than minus 2, because as we've already seen, if the value of x is less than or equal to minus 2, the mod itself will be greater than or equal to 2. So for mod of x less than a, I'll have to say that x will have to lie between minus of a and a. You can use the bracket notation also, bracket minus a to a. And over here, if a is a negative number, so mod of x less than minus 2, we'll again say the same thing, that mod of x cannot possibly be negative. So again, when a is negative, this inequality will have no solutions. Examples. So suppose I have this inequality, mod of 2x minus 1 is greater than 2. So that can either mean that 2x minus 1 is less than minus 2, or so x is less than minus 1 by 2. Right, so my solution set directly turns out to be that x can belong to the interval minus infinity to minus half union 3 by 2 to infinity, and similarly maybe I have something like this. So if mod of 2x plus 1 is less than or equal to 3, then 2x plus 1 itself has to lie between minus 3 and 3. Right? 2x plus 1 is between minus 3 and 3. 2x itself is between then minus 4 and 2, and x therefore itself is between minus 2 and 1. So again, of course, these equations and inequalities, these three examples that we have taken are very straightforward. We can have some more complicated expressions also, inequalities or equations also, but the principles kind of remain the same. Essentially, for modulus-based inequalities, what you have to keep track is that the inequality, the modulus as definition is always something which is greater than or equal to 0. Before we start off with solving modulus-based equations, there is one very important concept that we want to look at, and that is the idea of squaring both sides of an equation and inequality, and what is the condition under which you can basically do it. Right? So squaring, first of all, what you have to realize is first of all, what you have to realize is that you cannot always trivially square both sides of an equation or inequality. Squaring both sides might always lead to a situation in which the solution set of the original equation or inequality might change. So as a simple example, suppose you start off with the equation x minus 1 equal to 2. So obviously for this equation just has one solution, and that is 3. But if I were to square this equation, then the transformed equation is this, x minus 1 whole square equal to 4. So the solution set over here is the set containing the value 3 only, but over here, of course, since it's a square, x minus 1 itself could be plus or minus 2, which would mean that x could either be minus 1 or 3. So as you can clearly see that these two equations are not equivalent. So we say that two equations are equivalent if the solution sets happen to be, two equations will be, mathematical statements will be equivalent if the first implies the second and the second also implies the first. For two equivalent equations, the solution sets must be identical. So now what will happen? So clearly these two equations are not equivalent, because although the first statement implies the second does not necessarily imply the first. X minus 1 square equal to 4 can mean that x minus 1 is either plus 2 or minus 2, right? So that's why, as I said, the squaring both sides of an equation or inequality for that matter will not always trivially preserve the solution set. But an interesting observation is that if you have an equation or inequality in which it is known that both sides are positive, then squaring both sides will not affect the solution set. The solution set will remain preserved. So for example, if I knew that x minus 1 has to be a positive quantity, which means that x has to be a value which is greater than 1, then effectively squaring does not change the solution set, because you will anyway neglect the value minus 1. If I square both sides under the condition that x minus 1 itself is a positive value, then squaring will not change the solution set, because in that case again you will say that since you are getting minus 1, but minus 1 will have to be rejected, because for minus 1 the expression becomes negative. And the same thing works for an inequality essentially also. So if you have an inequality in which it is known that both sides happen to be positive, then squaring both sides will not affect the solution set. This is something which is very important. Emphasize again, re-emphasize, if you have an inequality or an equation in which we know that both sides happen to be positive, then you can square both sides without worrying that the solution set will change. Now this can be very useful in some modulus-based problems. So as an example, we'll be looking at modulus-based inequalities in some time, but just as an example, or let's look at an equation. If you have your equation, mod of 2x minus 1 equal to mod of x plus 1, and you want to solve it. So the way this idea could be used is that, first of all, by the definition of a modulus, obviously the LHS and RHS, both values are greater than or equal to 0, which means that again squaring will not change the solution set. So I can square both sides. And now I can use my property that again mod of x, if I square square of mod of x is equal to x square, essentially. We saw that property. So again, if you square a modulus term, then you can remove the mod effectively. So it becomes pretty simple. The values of x as 0 and 2. If we didn't use this method, we would have had to go to the idea of taking cases and solving the problem, which again is not very difficult, but this would be slightly shorter. So with these fundamentals in place, let's start looking at modulus-based equations now. So let's start looking at these questions. We could use the property that x square and mod of x square is the same, which means that I can replace x square by mod of x square, and once I do that, I simply get a quadratic in mod of x. So if I now put mod of x as some variable y, so I easily get the values of y as 2 or 1, and then substitute back. So mod of x equal to 2 is equal to 2, x can be plus minus 2, and if mod of x is equal to 1, x could be plus or minus 1. So it's turning out that this equation finally has a set of, it has 4 solutions. Right, so the answer is, in the first question we're getting a total of 4 solutions. Similar, so again I can replace x square by mod of x whole square. In the second one, when I solve for mod of x, I'll get my roots as minus 2 or minus 3, which we've already seen cannot have any possible solutions. Mod of x cannot be minus 2 for any value of x, and similarly mod of x cannot be minus 3 for any value of x. So for the second question, the answer will be a null set. It already is in quadratic form, so x plus 1 as y. Quadratic formula for the roots gives me 1 plus 1 as minus 1, which will not give me any real solutions. And for mod of x plus 1 equal to 3 by 2, I can say that x plus 1 will be plus or minus 3 by 2. So again, take the positive sign once. So that will give us 3 by 2 minus 1 by 2. And taking the negative sign once gives us solution set is half comma minus 5 by 2. We start by saying that mod of some expression is 3. So this expression could be plus or minus 3. And then we just have to take two cases, one with plus 3 and minus 3. We get two quadratic equations and we have to solve for those values. Roots as plus 2 minus 1, so minus 2 comma 1. Two solutions, minus 2 and 1. And if I take the negative case, real values of x, since x is the discriminant is turning out to be negative. In case of x square plus x plus 1 being equal to minus 3, it turns out does not give me any solutions. So the final solution set also is this itself. So x can either be minus 2 or 1. We have to now be careful. It wouldn't be right to say that since mod of 3x minus 1 is 2x, I directly cannot say that 3x minus 1 will be plus or minus 2x. Because over here the right hand side 2x is not it itself is a function, it depends on the variable x. So we'll have to kind of take different scenario cases over here. So one simple observation is that the LHS is a modulus based term, so it obviously is greater than or equal to 0 always. So for any solution to exist, then the right hand side also must be greater than or equal to 0. Right? So for any solution, anyway for values of x which are negative, we cannot get any solution. So x itself must be greater than or equal to 0. And once x is greater than or equal to 0, I can now say that under this assumption, I can say that 3x minus 1 itself is plus or minus 2x. Again, if I take the positive and negative sign separately, positive and negative sign, I'll get two values of x, 1 and 1 by 5. Right? And now I'll have to take an intersection of these two conditions. Of course, both these solutions will be acceptable. Since the condition was that x has to be greater than or equal to 0, I can effectively now say that both the solutions are acceptable. As a similar question, suppose the question had been mod 3x plus 1 equal to 2x. If this had been the question, and let's say you had proceeded by saying that 3x plus 1 is plus minus 2x, and therefore x can either be minus 1 or equation, if I had kind of said that 3x plus 1 is plus or minus 2x, and therefore x should either be minus 1 or minus 1 by 5, you would have saying that this is the answer minus 1 minus 5 by 5 would have been wrong, because again clearly for minus 1 and minus 1 by 5 both the RHS is turning out to be negative, whereas the LHS is something which is obviously greater than 0. So you would have had to reject both. Again, we can kind of take two cases. in fact, it's not even case. It's for we can start by imposing the condition that for a solution to exist, again the RHS has to be greater than or equal to 0. So being imposed because we are arguing that since the LHS is something which is always non-negative, the RHS will also have to be non-negative for a solution to exist. So that's why you get the condition that x itself must be greater than or equal to 0. Then again, once after this, now I can now say that. So again, take the positive and negative case. Quadratic, I'm getting these two values, 2 into 1 plus minus root 3. But again, clearly x needs to be greater than or equal to 0. So from here, I will only accept the positive sign root. Right, so the first possibility gives me only one solution, that is 2 into 1 plus root 3. And similarly, I can take the second possibility, 2 root 2. And again, x has to be something which is greater than or equal to 0. Right, so finally this equation has only two solutions, 2 into 1 plus root 3 and 2 root 2. If there had been a minus 2x over here, then of course you would have you would have said that x itself has to be less than or equal to 0. So in that case, you would have taken the negative value root over here and the negative sign over here. Seventh one, you actually have two terms with a modulus on them. Typically in such questions, we'll have to take multiple cases. But in this specific question, that can be avoided by observing that x square plus x plus 1 will always be positive. Right, we had kind of covered this concept in quadratic equations. A quadratic expression ax square plus bx plus c, if for this expression the b square minus 4 is c value, the discriminant happens to be negative, then this expression always has the same sign, and which depends on the coefficient of x square. So if coefficient of x square is positive and d value is negative, then the expression will always be positive. And if the coefficient of x square is negative and the d value is negative, then the expression will always be negative. So therefore clearly over here the d value is minus 3 and of course the coefficient of x square is plus 1. So the expression x square plus x plus 1 we can therefore say will always be positive. And since it is always positive, I can anyway trivially get rid of the modulus sign. So that just then leaves me with one modulus sign. And now at this stage I can take two cases. The first case is, again, this expression will change its sign at 3 by 2. So one case will be that x is greater than or equal to 3 by 2. Under this condition, the equation reduces to this form. Plus 3x minus 4 is minus x minus 2 equal to 0. So x itself could be either be 2 or minus 1. But now again, you cannot trivially accept both the solutions over here. We can only accept solutions which satisfy this condition because this is the assumption under which you were solving the problem. So minus 1 will clearly have to be rejected therefore. So right, so this is important. Again, the reason why minus 1 is being rejected is because it is not satisfying this particular condition, which was the condition under which you had simplified the problem and you were solving it. That's why the only solution that you will accept is 2. If hypothetically both the roots had turned out to be less than 3 by 2, then you would have rejected both the values. And if both the roots had been greater than or equal to 3 by 2, you would have accepted both the roots. Right? But in this case, we will only be accepting x equal to 2. Similarly, the second case, my second case is that x itself is less than or less than 3 by 2. So what will happen over here? That gives me x square plus x minus 2x minus 4x. So that's x square minus 5x plus 4. So I get the values of x as 1 or 4, but then again 4 has to be rejected because it does not satisfy this condition. Right, so our final analysis is that there are only two solutions, 2 and 1. So now in the 8th problem again we have two terms on which we have the modulus operator. But now over here we'll have to actually take multiple cases. Right, so again the first term changes its definition at -1 and the second term changes its definition at 3. So essentially there will be two cases. We'll have a set of values of x which are greater than equal to 3, then we'll have values which are greater than equal to 1 and less than 3, and finally we have values which are less than 1. So case 1 again is, now under this condition what does the equation become? 2 times x plus 1 plus x minus 3 is equal to 4. That will be 2x plus 3x. 2 minus 3 is minus 1 equal to 5. So under this condition when I solve my equation, I get x as 5 by 3. 2 into x plus 1, 2x plus 2, 3x plus 2 minus 5. And if you now observe, this value will have to be rejected because 5 by 3 does not satisfy this condition. 5 by 3 will be less than 2. So 5 by 3, since it does not satisfy the condition of x being greater than equal to 3, this value has to be rejected. In the second case, again I'll assume that x and take back, this is minus 1. The first term will change its definition at -1, not at 1. So the second case will be that x can be greater than equal to -1 and it is less than 3. Now for these values of x, again the first term remains x plus 1. The second term will be minus of x minus 3. Since x minus 3 will itself now be negative. So again solving, I get 2x minus x, so that's x plus 2 plus 3 plus 5. Solving here x as -1 and x equal to -1 clearly is satisfying this condition. So that is another solution. So that is the first solution in fact. So the second case does give us one solution, and that solution is x equal to -1. My third case would be that I am considering those values of x which themselves are less than -1. So under this condition again, first term becomes 2 minus of x plus 1 minus of x minus 3. So that will be minus 2x minus x minus 3x minus 2 plus 3 plus 1 equal to 3. So the third case again gives us x equal to -1. Now to be very specific, as far as case 3 is concerned, x equal to -1 has to be rejected because case 3 was solved under the condition that x is less than -1. But it doesn't matter because x equal to -1 has already been accepted overall as a solution from case 2. So the final answer is that the final analysis would be that there is only one solution, and that is x equal to -1. And the ninth question, let's try to first factorize the second expression. So -10, and so we'll get a +5 and a -2. Right? So from here I get one solution definitely as x equal to 1, and another possibility is that right, so one solution definitely is x equal to 1, and the other possibility is that this bracket is 0, which effectively says that mod of x square minus 4x plus 3 must be equal to -2x minus 5. Right? Again, we can either take two cases that depending on whether this expression is greater than 0 or less than 0, greater than equal to 0 or less than 0. Another thing that we could do again over here is that observe that for a solution, for this equation to have a possible solution, the RHS should be greater than or equal to 0, which itself will tell us that x itself has to be less than or equal to minus 5 by 2, right? So now what I could do is I could say that, right? So again, let's take the positive sign once. So minus 2x minus 5, so x square, sorry, this would be x square minus 4x minus 2x, so that's minus 2x plus 8. This equation of course does not give me any real solution since the discriminant itself is negative, so I'll take the other sign over here now. So x square minus 6x minus 2 equal to 0 gives us that x is 6 plus minus under root. The discriminant should be 36 plus discriminant should be 36 plus 8, so that's 44, right? Right now, but over here, if you observe again, when you take the positive sign, you're obviously getting a positive value, which clearly does not satisfy this first condition. So the positive sign root will be rejected. And if I take the negative sign root also is not satisfying this condition, because root 44 will obviously be less than 7. So this entire value is, this entire value is definitely greater than minus 1 in magnitude. This entire value is less than 1 in magnitude. Right, so again, since both these roots do not satisfy the first condition, this condition that x is less than equal to minus 5 by 2, over here, this case also does not give you any solutions. So finally, so what is the final analysis? There is only one solution, and that is x equal to 1. X equal to 1 is the only solution. In the 10th question, before we do anything else, we should first impose a condition that x is not allowed to take the value 1. And that is clearly because if x is equal to 1, the denominator becomes 0, which is something which is never allowed when you're solving equations and inequalities. So again, as a habit, whenever you have a situation in which you have an expression in the denominator, you first should ensure that no value of x for which the denominator is 0 can be accepted. Right? So in the 10th question, the first thing that I'll say is that x cannot be equal to 1. Because again, if x is equal to 1, then the inequality, the equation will not be defined. After this, we can use some properties. The modulus will get distributed over here. Mod gets distributed and x square can be replaced by mod of x whole square. So if I cross multiply, I get mod of x. Right, so cross multiplying gives me that mod of x into 1 plus mod of x minus 1 is equal to mod of x whole square. So again, there's a common factor on both sides, which is mod of x. So one possibility is that either mod of x is 0 or 1 plus mod of x equal to 0, of course, gives me that x is equal to 0. So I've got one solution which is x equal to 0, and for other solutions I'll have to go back to this equation now. So again, now if I look at this equation, in this equation there are two modulus based terms. The first one, this changes its definition at 1. Mod of x itself, of course, will change its definition at 0. So again, there are three cases that I'll have. In the first case, suppose x itself is greater than or equal to 1. So the mod x minus 1 is x minus 1, mod of x is x. So in the first case, I get the statement that 0 is equal to 0. So what that basically means is that the equation is getting satisfied for all possible values of x, right? So it turns out that for any value of x which is greater than equal to 1, the equation will definitely be satisfied. So again, interestingly, all possible values of x which are greater than or equal to 1 satisfy the given equation. Second case, of course, if x is greater than equal to 0 and less than 1, so mod of x minus 1 becomes minus of x minus 1, and mod of x remains. So the second case I get x is 1, which has anyway already been included, and specifically to this case 1 has to be rejected, but 1 has already been included, so that's okay. And our last case itself is that x must be less than, let's suppose x is less than 0. So under that condition, again mod x minus 1 becomes minus of x minus 1, and mod of x becomes minus of x. So you get a statement which is 2 equal to 0, which obviously is false, which means that what the interpretation of that is that for any value of x which is less than 0, the equation is not satisfied, right? So the third case again does not give you any solutions. So in your final analysis, they are essentially you can have x as either 0 or x can take any value which is greater than or equal to 1. So our final answer then is right. So x can take any value which is greater than or equal to 1, or it could also be equal to 0. Sorry, x we had already kind of written in the starting. In the beginning, we had written that x itself cannot be equal to 1. So over here, we cannot accept 1. Right, 1 as we had written now in the start, if x is equal to 1, the equation itself will not be defined, and therefore you cannot accept x equal to 1. So you have to reject it. So the 11th question, as a first step, as I've just made a very simple substitution, I just substitute x minus 1 as the variable y. So in the variable y, the equation reduces to this now. So we'll try to solve for y, and then once we get the values of y, we can obviously easily get the values of x. Over here again, there are two modulus based terms. So the first thing would be to identify the values of y at which each term changes its definition. So mod of y plus 1 will clearly change its definition at minus 1. And this term, of course, will change its definition when two raised to y minus 1 will clearly be 0 when y is equal to 0. So again, there are two values of y at which the equation is changing, at which the terms will change the definitions. So one is y equal to 0 for this term, and for the first term, y, it will change its definition at y equal to minus 1. So again, we'll kind of take three cases over here, right? So again, if y is greater than equal to 0, mod of y plus 1 will obviously be, y plus 1 will be greater than equal to 0. So if y is greater than equal to 0, then this entire term is greater than equal to 0. So again, you get a statement which is true for all values of y. So it's turning out that when y itself is greater than or equal to 0, the equation will always get satisfied. So y greater than equal to 0 is a part of your final solution set. And if y is greater than equal to 0, that would mean that x must be greater than or equal to 1. So any value of x, so what's turning out is that any value of x which is greater than or equal to 1 is definitely satisfying the equation. Just look at case 1 again. Our second case would be that y is less than 0 and greater than equal to minus 1. Now under this condition again, mod of y plus 1 remains y plus 1. But now 2 raised to y minus 1 becomes negative, so this will be minus of, right, 2 raised to y minus 1 itself becomes a quantity which is negative, so its mod will be minus of 2 raised to y minus 1, so effectively there is a positive sign outside. So that gives us y as being 0, but then again y equal to 0 does not strictly satisfy this condition. So as far as this condition is concerned, we can reject it, but again just keep in mind that y equal to 0 has already been included from the previous case. So our last case is that y is less than minus 1. The third case, again, mod of y plus 1 will be minus of y plus 1. The second term is 2 raised to y minus 1, gets cancelled. So solving, I finally get y as being minus 2, which again is acceptable because it satisfies the assumption. And if y is minus 2, then x itself must be y plus 1, so minus 1. Right, so this is another solution that we've been able to find for the system, that x is equal to minus 1. So our final solution set therefore must be that our final solution set is that x can take values which x can take any value which is greater than or equal to 1. Right, x can either belong to the interval 1 to infinity, or it could also be equal to minus 1. So we've now seen modulus-based equations and different techniques of solving them, and now let's go to modulus-based inequalities. So before we go on to modulus-based inequalities, just want to re-emphasize some ideas that we've already discussed. First, under properties of modulus, we had seen that if mod of x is less than a, where a is a positive value, I can say that. So again, I'll just write those inequalities again, which I had written down when we were discussing properties of modulus. So mod of x less than a, I can say that effectively x lies between minus a and a, assuming of course a is positive, and mod of x greater than a will have a solution set of again, this is also assuming that a is positive. And for a negative, as we already discussed, mod of x less than a, if a is negative, will actually correspond to a null set, cannot happen. And similarly, mod of x greater than a, where a itself is less than 0, will correspond to the set of all real numbers. And another idea that we had discussed in squaring both sides of inequality was that if you have an inequality in which it is known that both sides happen to be positive, I can square both sides and the solution set will not change, right? So let's use these basic ideas and look at how quadratic inequalities can be solved. Modulus-based inequalities can be solved. Right, so let's start with these problems. For the first one, modulus of some expression is less than minus 1. As we already discussed, modulus of anything is always greater than or equal to 0, so it obviously cannot be less than a negative number. So the first question, the answer should be a null set. Right, so for question number 1, the answer should be a null set. For the second question, you're saying that modulus of an expression is greater than or equal to minus 1. Modulus of any for all values of x, mod of x square minus 1 will anyway be greater than or equal to 0. So it obviously will also be greater than or equal to minus 1. So for the second problem, your answer is effectively the set of all real values. Okay. For the third problem, we could kind of go in a step-by-step manner. We could start by substituting mod of x minus 2 as some y. So mod of y is less than or equal to 3, but we already know from that y will lie between minus 3 and 3. Right, if mod of y is less than or equal to 3, then y has to lie between minus 3 and 3. Replace the value y back, so mod of x minus 2 is between minus 3 and 3. So mod of x must be between 5 and minus 1. Now mod of x greater than or equal to minus 1 anyway is always true, right? So this effectively means that mod of x is less than equal to 5, which itself will happen if x is between minus 5 and 5. So for the third inequality, our answer should be that the variable x can take any value between minus 5 and 5. Similarly, for the fourth one, if you want, you could substitute mod of 2x plus 1 as some variable y. So we get mod of y minus 1 is greater than or equal to 2, but then again that could mean that y minus 1 is less than equal to minus 2, or again substitute the value of y back. So mod of 2x plus 1 is less than equal to minus 1, or but then again this cannot happen. This inequality will clearly give you a null set. And going back to the second part, mod of 2x plus 1 is greater than equal to 3. So again 2x plus 1 can either be less than equal to minus 3, or again if mod of x is greater than or equal to a, where a is positive, you can directly say that x must be less than equal to minus a, or x must be greater than or equal to a. So then this is our final solution set. So final answer is that x can take values less than equal to minus 2, or it can take values which are greater than or equal to 1. Now the fifth inequality says that mod of x minus 2 upon x minus 2 should be greater than 0. So again, as a first step, we should definitely say that x cannot be equal to 2. X is not allowed to take the value 2, since if x is equal to 2, the denominator will not be defined. Now one simple observation is, of course, you can take two cases if you want that x is greater than 2 or less than 2, but that's not really required. As long as x is not equal to 2, mod of x minus 2 obviously is a quantity which will always be positive. So mod of x minus 2 is positive for all x. And since it's always positive, I can divide both sides by mod x minus 2. Or in other words, since mod x minus 2 is positive, since mod x minus 2 upon x minus 2 is positive and mod x minus 2 is anyway greater than 0 as long as x is not equal to 2, I can divide both sides by mod x minus 2. So 1 upon x minus 2 has to be positive, which will obviously only happen if x minus 2 is positive, which will happen if x is greater than 2. So this should be the final answer as far as the fifth question is concerned. The sixth question is kind of similar. So again, x should not be equal to 2 is the first condition, because again the denominator is not allowed to be 0. Now, since this expression has to be less than or equal to 0, we can just quickly split it up into two possibilities. It's either less than 0 or equal to 0. If it's equal to 0, then x can only be equal to 3. Clearly, if x is equal to 3, the numerator will be 0, so the entire expression is also 0. Now, if x is not equal to 3, then again my inequality is mod x minus 3 upon x minus 2 is less than or equal to 0. But since x is not equal to 3, I can divide by mod x minus 3 on both sides. Since mod x minus 3 will be positive. And again, as we've discussed, when you divide both sides of an inequality by a positive quantity, then the sign of inequality will remain the same. And of course, for this to happen, x minus 2 itself must be negative. Right, so from 1, 2 and 3, our final solution set should be x can take all values which are less than 2, and additionally it can also take the value 3. Right, x can take all values less than 2, or it could be equal to 3. For the 7th question, again we should start by saying that the denominator is not allowed to be equal to 0. So x minus 4 should not be equal to 0. After that, distribute the modulus. Now since as x is anyway not allowed to be equal to 4, and as long as it's not equal to 4, mod of x minus 4 will always be positive. So I can kind of cross multiply on both sides by mod x minus 4. And then we can use the standard form. Mod of an expression is less than 2, so that expression has to be lie between minus 2 and 2. So x will have to lie between 2 and 6. But then now you have to be careful. The final answer is not that x can lie between 2 and 6, because clearly x cannot be equal to 4. So from 1 and 2, so x can take values between 2 and 6 except 4. So this will be our final answer. X can take values between 2 and 6, and of course it is not allowed to be equal to 4. Now in the 8th one, there are two approaches that you can take. You can either take the 3 cases, since there are 2 terms with modulus signs. You can take those 3 cases greater than equal to 3, greater than equal to 2, less than 3, and less than 2. In this case, there's a simpler way also by using the idea that we discussed. You have an inequality in which there's a mod on both sides. So both sides by definition are positive, greater than equal to 0. So I can square both sides and the solution set will not change. Right? So I easily get my answer as the set 5 by 2 to infinity. But then again, it is important to note that the squaring over here is possible because you know that both sides happen to be positive. For the 9th question, again, we could start by first saying that the denominator should not be 0. Which means that x cannot be plus or minus 2. Then distribute the modulus. Again, as long as x is not equal to plus minus 2, mod of x square minus 4 is always positive, so cross multiply. And since now again both sides are positive, I can square. But again, we won't expand after squaring, that won't really help. So get all the terms to one side and factorize. And at this stage we have we could now obviously use the wavy curve method. You have a rational polynomial expression, factorize it further. So this is x plus 4 into x minus 1. This is x minus 4 into x plus 1. Right, so we have a product of 4 linear factors greater than 0, so it's easily solvable. So by the wavy curve method, what are the critical points over here? Minus 4, minus 1, 1, 4, powers are anyway 1. So you want the expression to be positive. So for the expression to be positive, the wave should be above the axis. So that will happen from minus infinity to minus 4, union, minus 1 to 1, union, 4 course the interval, the final answer should not contain the points -2 and 2, which it doesn't. The 10th question is a little tricky, we'll have to be careful with it. You cannot, first of all, it's important to realize you cannot simply square over here and get all the terms to one side and factorize. In this case, trivially, because again, we had said that the squaring both sides can be done. You can be absolutely sure that the squaring will definitely not change the solution set if you know that both sides of the inequality happen to be positive. If you don't know that, then the solution set might change when you square both sides. So over here, since this expression can both be positive or negative, we shouldn't really square. So let's take two cases. So the first case is that suppose 2x square minus x is negative. So now think about this. If 2x square minus x is a negative quantity, then obviously the given inequality will have no solutions, because modulus, if anything, cannot be less than a negative number. So there will be no solution. So we can anyway solve under the assumption that 2x square minus x must be greater than or equal to 0. Any solution set that you finally get must belong to this, must satisfy this condition. So that is effectively saying that right? So the final solution set therefore definitely must be a subset of this particular set, right? The final values of x that you get should definitely satisfy condition number 1. Now once I assume that, of course, once I am operating under the condition that 2x square minus x itself is greater than or equal to 0, I can now square both sides and then factorize. When I factorize, I get this product. This expression, of course, minus 15, and let's just really check our calculations again. 2x square minus x whole square minus, this should be a minus 15. An interesting observation is that the second quadratic expression is anyway always going to be positive, because again the d value is negative. So right, so the second quadratic expression is always going to be positive, d value is negative, coefficient of x square is positive, and since it's always positive, I can divide by the expression on both sides. So effectively, I'm only left with this solution, this inequality. So you can factorize it easily. Right? So 3x plus 5 into x minus 3 should be positive, which again by the wavy curve method will give us that so we finally, again, let's just quickly go over the entire flow again. We first said that you can anyway talk about a solution will exist only as long as the RHS is greater than or equal to 0. So I said that 2x square minus x must be greater than or equal to 0, which gives us this set. Under the condition that the RHS is also greater than or equal to 0, we squared both sides, got all the terms to one side, factorized. This expression was always positive, so divided by it on both sides, and I get this as my solution set. The final answer, of course, should be the intersection of 2 and 1. And the intersection of 2 and 1 is turning out to be the second set itself. Right, so final answer should be the variable x can take values which are less than minus 5 by 3, or it can take values which are greater than 3. 11th question is kind of similar. Just distribute the modulus. Square. Since anyway both sides are positive. Factorize 2x square plus x into let's factorize further. So we get x into 2x plus 1 into x plus 2 is positive. Again, wavy curve method. Critical points are -2, -half, 0. Right, so you want the expression should be positive, so the wave should be above the axis. So final answer should be between -2 and -half, or from 0 to infinity. So in the 10th one again, we should start by 10th one is again a pretty straightforward problem. So we should start by obviously saying that x should not be equal to -4. And since again, as long as x is not equal to -4, mod of x plus 4 will anyway always be positive. Again, cross multiply by mod of x plus 4 on both sides. So cross multiply by mod x plus 4 on both sides. Quadratic inequality factorized wavy curve method. The answer is -7 to 1. But again, you have to take an intersection with 1, so x should not be equal to -4. So from 1 and 2, the answer should be that x can belong to the interval -7 to -4 union -4 to 1. So x can take any value between -7 and 1, but of course it cannot take the value equal to -4. And the 11th question, the inequality, if we factorize the denominator, reduces to this particular form. So again, from this form, the first thing that we'll say is that the value of x should neither be equal to 2 nor can it be equal to 3, because again the expression will not be defined. So we can take two cases now. X can either be greater than 3 or it could be less than 3. So if x is greater than 3, then this is the inequality. So I can cancel out the common factor. From what we have discussed, we have to be careful. You cannot cross multiply by x minus 2 because x minus 2 could be positive or negative both. So the idea would be to get all the terms to one side. When I take all the terms to the right hand side, this is the reduced form for the inequality. Again, you can the wavy curve method would be applicable over here. So by the wavy curve method, the answer is x lies between 2 and 5/2. But now again, I have to take an intersection of 3 and 4. This is the solution set under the condition that x itself is greater than 3. But clearly from 3 and 4, there is no intersection. So from statements 3 and 4, you get that there are no such values of x. So case 1 effectively does not give us any solutions. So we'll now have to go on to case 2, for which x is less than 3. So again, if x is less than 3, then mod of x minus 3 will be minus of x minus 3. Again, cancel out x minus 3, take all the terms to the right hand side. If I simplify, I'll get 2x minus 4 plus 1, so minus 3. Right, I get 2x minus 3 upon x minus 2 is negative, which again by the wavy curve method gives me that. So the wavy curve method gives me that the values of x can be between 3 by 2 and 2. And now I'll have to take an intersection of 5 and 6. Actually, I have to take an intersection of 2, 5 and 6. Right? So from 2, 5 and 6, then again, if I take an intersection of 2 and 5 and 6, I'll get this set itself. 3 by 2 to 2. Right, so again from 2, 5 and 6, x can take values between 3 by 2 and 2, and that is also then our final answer. Now the 12th question is kind of, again, it's slightly tricky, we'll have to be careful. We'll have to basically, there is no other way, we'll have to take multiple cases. There are 3 modulus terms over here. Again, changes definition at 1, minus 1 and 2. So that's why we'll now have to take 4 cases. So which are our 4 cases going to be? Values of x greater than equal to 2, values of x greater than equal to 1 less than 2. In the third case, values of x greater than equal to minus 1 and less than 1. And the last case, values of x which are less than minus 1. So let's look at the first case. It's always a good habit to write down your modulus terms in increasing order in which the critical points occur. Right? So for x greater than equal to 2, all the expressions will be positive. So I get 2x plus x plus x, so that's 4x. 2 minus 2, 0 is less than. So I get x is less than equal to 9 by 4, but then again I'll have to take an intersection of 1 and 2. Statements 1 and 2. The first case gives me these set of values, allowed values, that x can take values which are greater than or equal to 2 and also which have to be less than or equal to 9 by 4. Right? So that is of course part of the solution set. The second case, I am assuming that x takes values between 1 and 2, it's greater than or equal to 1 less than 2. Under this condition, these are the modulus terms. Only mod x minus 2 will be minus of x minus 2. Solution set that I get is x less than or equal to 5 by 2. Again, we'll have to take an intersection of 4 and 5. So that should give me the set 1 to 2 itself. So the second gives, so all values of x corresponding to the second case are part of the solution set of the inequality. Our next case would be the set of values which are greater than equal to minus 1 and less than 1. So again under this condition, in the third case, again, when you solve the inequality, it's turning out to be identically true. So this the 5 is obviously less than 8. So this is true for all values of x, which effectively means that all these values, all values of x between -1 to 1 are part of the solution set. And finally, the last case. So in the second case, I get my set of values as x greater than equal to -7/4, which you again have to take an intersection with statement 9. So right, so now if we take a union of all the solution sets, if we take a union of all the solution sets, I'm effectively getting the interval. So -7/4 to -1, union -1 to 1, union 1 to 2, and union 2 to 9/4. So the final answer effectively is -7/4 to 9/4. So this kind of, we've completed the concept which we've completed the idea of the concepts which cover modulus, the idea of modulus and modulus based equations and inequalities. So that from your booklet perspective covers CCP 6 and 7. So these are some questions that you could try on your own. All these questions would involve all the concepts that we've discussed right now. Completes the concept on modulus based equations and modulus based inequalities. Thank you.